So in the earlier lecture I derived Simpson's rule using Newton-Cotes quadrature formula, but in today's lecture I will derive Simpson's 1/3 rule with the help of a polynomial or with the help of a parabolic approximation. Means second order polynomial I will use to derive it, right? So consider a graph just like this. That's what we have to keep in mind, and the curve is like this, and say this is the point x0, say it is a point x2, and this is the midpoint, it is x1, and x1 is such that it is x2 minus x1. It is the midpoint of x2 minus x2 plus x1 divided by 2. It is the midpoint, right? So that means this separation is h. This point is also h, and if we call it as 0, then this point will become minus h and this will become plus h. And we have to find the complete integral from here to here. But first of all, let us approximate this region and say this is the one region, and do one thing. Say this curve is replaced by some parabola. Means in this region we will define a curve and let us call it as ax square plus bx plus c. It is f of x, it is second order polynomial, it is ax square plus bx plus c. This is the parabola. Okay, so that means this region is approximated by using this one. So now the integral, and let us call this region is basically I1, right? So I1 we are interested to find it out. So I1 is basically is equal to, it is f of x, it is from x0 to x2 dx, and to find out the integral of the whole region I will generalize this right later on, and say this is approximated by this second order polynomial, right? So it is f2x dx, right? And what is it f2x? It is a x square plus bx plus c dx. It is x0 to x1, sorry, not x1 but x2, sorry, right, it should be 2. And let us find out its integral. Now if I find out the integral, then this will become ax cubed by 3 plus bx square by 2 plus cx, and integral from x0 to x1. Keeping this thing in mind, let us change the limits. So rather than using x0, x1 and x2, we can use minus h2 plus h, right? Minus h2 plus h. So if I put these limits, so then it will become ax cubed by 3 plus bx square by 2 plus cx, it is from minus h2 plus h which we are using. So if I put these values here, so what can I do? Upper limit is h, so ah cubed by 3 plus bh square by 2 plus ch minus a minus h cubed by 3 plus b minus h square by 2 plus c minus h. That's what we are getting. It is ah cubed by 3 plus bh square by 2 plus ch, it will become minus minus plus, so it is ah cubed by 3 minus bh by 2, bh square by 2 plus ch, right? So this will cancel out with it. So it is 2a by 3h cube plus 2ch. That's what we are getting, right? So this integral is basically I1 is nearly equal to this one. So here if I take h by 3 common, so inside it is 2a by 3 plus 6c we are getting, right? So now our objective is to determine this value, that what is its value, right? So to find out its value, let us proceed as follows. As we know that the points x0 f0, x1 f1 and x2 f2, that is, this can be replaced by plus minus h, this is replaced by 0 and this is replaced by plus h. That is the points minus h f0, 0 f1 and plus h f2, they all lie on chosen parabola or chosen quadratic equation, quadratic polynomial, that is ax square bx plus c. So if I put these values here, then what we are getting f of naught is equal to, it is ah square minus bh plus c. I have used this point, then f of 1 can be written as c and f of 2 can be written as ah square plus bh plus c. Let us call it as equation number 2, equation number 3, equation number 4. So what I need to find a 2a by 3. So for this, let us proceed as follows. Let us use the operation 2 plus 4. If I add these two equations, then f naught plus f of 2 can be written as, these two will cancel out, so it is 2a h square plus 2c we are getting, right? That's what we are getting here. Okay, sorry, when I take h by 3, so yeah, let us, it is h square, right? Yeah. So now what we need, 6c. So what I will do, I will now apply the operation that 5 plus 4 times the equation 3. If I use this, then what I am getting, f of naught plus f of 2 plus 4 f of 1 is equal to 2ah square plus 6c, right? That's what we are getting. So now I will put its value in equation number 1, right? So therefore the integral I1, it is h by 3 2ah square by 3 plus 6c, it is equal to f of naught, it is h by 3 f of naught, f of 2 plus 4 f of 1. So this can also be rearranged in a way that means the integral f of x dx x naught to x2, let us call it as I1, and it is h by 3 f of naught plus 4 f of 1 plus f of 2. That's what we are getting, right? So in the first region we have defined it, and now we will generalize it, right? Now we will generalize it. So let us generalize it to find out the complete integral. So complete integral, as we have also talked about in the earlier lecture, that I is basically is equal to x naught to xn f of x dx, and it is x1 to x naught to x2m f of x dx, and it can be written as x naught to x2 f of x dx. Now it will become similar as we have talked about in the earlier lecture, x2 to x4, f of x dx plus and so on, x2m minus 2 x of 2m, it is f of x dx, and it is equal to h by 3 f naught f1 4f1 and f of 2 plus h by 3 f2 plus 4 f3 plus f of 4 plus and so on, and plus and so on, h by 3 f of 2m minus 2 plus f of 2m minus 1 plus f of 2m, and this can be written as h by 3 can be taken, these all odd terms are occurring 4 times, so if they are occurring 4 times, then it can be written as, this will remain as it is, plus 4 f1 f3 and so on f2m minus 1, and this along with this is occurring 2 times, that means twice of f of 2 f of 4 and f of 2m minus 1 2, and this will remain only this is occurring only 1 time. That's what we are getting here, right? So this is all about it, right? Hence the Simpson's 1/3 rule. So that's all for this lecture. Thanks for watching this lecture, and in the next lecture I will use the Newton Cotes formula to derive Newton